Yeah, first of all, thank you very much for the invitation. Yeah, I came from Tokyo just for this talk, basically. I arrived yesterday and I fly back tomorrow morning. So I really want to hear from you. So I'll stay here after this talk and I also get questions during my talk. So please, please let me hear your voice. So I'm working on somewhere between HCI and graphics. I try to balance between these two fields. So for HCI, I want to make computers or computer systems easier to use. And in computer graphics, I'm more interested in like 3D shape processing and also communications using graphics. And here's a kind of background or motivation of all the works in our group. So this is very general discussion, but this society today is a mass production, a mass consumption, and we do see the same thing all over the world. I see IKEA shops everywhere in US, in Japan, or China, or Europe, the same thing. And also, same garment stores or electronics, well, it's the same cars. And this may be efficient, but I don't think it's very interesting. So one possible future vision is that everybody, end users, become designers and producers, and then they create things, satisfy their own needs. And obviously, this is not really new vision. Many people say the same thing using different keywords like computer-generated contents or prosumers or third or fourth in industry revolution. And there are already existing platforms to support this kind of activity like 3D printing or laser cutting. However, the problem is that it's easy to share existing shapes or designs or print and get it and use it, but still we believe that design or creating something new by yourself is still difficult. And that's a problem we want to address. So our goal is to help people design and fabricate what they need. And then we want to develop computers too to achieve this goal. So that's the goal. And then let me go more into details. So this is, I know, just too much simplification, but typical pipeline of computational design is like this. So users give requests to the computer, and then computer run some logic like optimization or something, and then you will get something result. And we are talking about artifact can be graphics like images and shapes in computers, or this can be a physical object like garments or chairs or anything. And then in the computational tool can be optimization, simulation, machine learning. However, in this typical traditional view, not much interaction after system gets requests. So what we want to do in our series of projects is a human-in-the-loop computational design, which means we want to integrate more human in this process. And so that's the view. And there's a certain benefits in this way of doing compared to fully automatic one. The first one, most importantly, is we want to support creative exploration, right? People not really knows what they really want at the beginning. So it's very difficult to give requirements clearly before you start working on it. So that's one important part. So you want to support creative exploration. And then even if the goal is clear, it may be difficult for computers to do it alone. So we want to exploit human perception, and also we want to exploit human body capability in the fabrication process. So that's the introduction. So now let me move into the specific projects we are working on with students. And honestly, not so organized. Maybe each student in my group work on different things. So just a collection of many different things. But I hope you see some consistent taste or vision behind them. So the first block of project is design with physical simulation. So the idea is like this. So computer-aided design. Designing something in computer is not new. So, people design everything in computers today. But still, most existing design tools doesn't consider physics during design phase. So it's basically just drafting or drawing software. You just put arbitrary lines, boxes, lines, and shapes, but they don't care about simulation. Simulation often comes later after you get something, and then move on to simulation, and then maybe go back later. But this cycle was not so close. So what we want to do is to integrate real-time physical simulation into a design system so that you get instant continuous feedback from the system to design some physically functioning objects. The first project we worked on, one is this kind of plush toy design system. So if you want to design a plush toy, you have to consider both 2D pattern and then resulting 3D shape, which may be easy for experienced people, but for novice users, for kids, it's very difficult. So we integrate kind of simple physical simulation to predict 3D shape from 2D pattern, and then you get a very nice design system. And that's a video. So it's fine. So the interface is taken from what's happening. The interface is taken from sketching interface modeling one. So you sketch something, and then you will get a 3D shape here. But at the same time, system also automatically generates 2D cross pattern for creating this stuffed animal. So internally, we run some basic simulation to predict the 3D shape taken from this 2D pattern. And then we implemented a couple of gestural interactions to get 3D shape. And then you eventually get reasonable stuffed animal here, 3D one, and then also you get a 2D pattern. So after finishing design, you can print this pattern and then cut cross material and stitch together and push cotton in it, and then you will get a 3D shape. And then here is the result. So yeah, after some editing operations, you can get reasonable 3D shape here. And then you get, I don't show here, but the system also shows which one is connected, which edge, and so on. So it provides some guide. And then you eventually get reasonable 3D shape. And then after spending some hours, then you get physical stuffed animal as well. And using the same pattern, you can also make a big balloon, you will see here. Yeah, again, traditionally, design of this kind of thing requires professional experience and knowledge. But with this tool, you just get something you want, and then you get physical stuffed animal. And we did some small user study. We provided this tool to kids, and they successfully generated their own customized one-of-a-kind stuffed animals. Traditionally, it's very difficult to design new ones. So they usually just buy existing template, and they just created a copy of some existing animal, stuffed plus toy. But here, these are their own, their own lovely, stuffed animals. And also, we found that this activity is very nice family event. Family members work together. Someone working on computer system, and then some people working on the swing, and it was a nice experience. So that's one thing. Okay, so next one. So next one is a kind of strange problem we want to address, but suppose you want to design a customized musical instruments, in this case a metalphone with special shape. And please also imagine that this is a very difficult problem, right? It's very hard to predict which sound each bar produces without actually fabricated and hit this bar. However, a computer can predict the sound. So we integrate physical simulation into the design system so that people can design musical instruments that produces appropriate sound and also have a nice look. So that's the idea. And
feedback inputs it. In this example,
so this is a design system. So here, the user is designing a bar of a metalphone, and the system runs real-time physical simulation, predicts the tone. And this is a visualization of a vibration, and also system gives audio feedback.
Metalphone is calculated via eigenvalue analysis. As the user edits the metalphone shape in the left window, the system immediately computes its eigenmode, showing the right window, which tells how the metalphone oscillates in 3D space.
So we believe that it is critical to provide continuous real-time feedback to assist the direct manipulation
in the status bar.
Design process.
Because the change of tone caused by the shape edit is very difficult to predict, we believe designing a metalphone with a desired shape and tone.
So this visualization is also important to identify where to fix this metal bar into the base.
will be possible only with a responsive FEM.
Yeah, and here is some results.
Here are the designed metal phone pieces by an artist.
And then we actually
and its actual creation.
Yeah,
this shows that our analysis successfully simulates the real world.
Yeah, but however, the one problem is that if you look carefully, this kind of strange shaped plates produces different tone depending where you hit. So you have to carefully hit specific place. If you see the video again, these guys carefully hit very specific place, right? Yeah. So
this shows that our analysis successfully simulates the real world.
Yeah. So again, this visualization tells you where you hit. The highest vibration point is where to press. So possible next project is to have a single plate and then produce different tone depending where you hit. That's one possible direction to go. But that's it. Okay. And we apply the same idea to a garment design. The idea is exactly the same. The user continuously edits the 2D pattern and the system continuously presents a simulation result to the user. Yeah, pajama for armadillo. So yeah, the user edit to the garment pattern here, and then system continuously provides prediction in the draping simulation result. Traditionally, this kind of design is done physically. People cut clothes and they put it on the mannequin, and they see the result and go back to the pattern. But here, you can just continuously see the result of wrinkles. If it's too tight, it's loose here, and then you get immediate feedback. If it's too short, and then gets the shape, and you immediately get the result. And I think this is very helpful for creative exploration. So maybe trivial or easy to, experts may not need this, but novice, non-experienced user can't imagine this in their heads, but this kind of visualization is very helpful. And this kind of tool is particularly useful for strange garments like pajama for armadillo. No one knows how to design a shirt for this guy. So real-time physical simulation is very helpful. Games are getting more and more sophisticated, and they often use physical simulation. Then physically realistic garment is necessary for this kind of strange guys too. And we actually fabricated this, and of course it's not exact perfect match, but you can see overall shape is reasonable. And we also created real garment. Yeah, reasonable thing. And then eventually you get a final result. Where is it? Yeah, it takes a certain amount of time. But yeah, so we made this. Yeah, he's rotating by himself. We don't have a nice studio. That's fun. Okay, let me move on. So this is, again, another craft work. Suppose you want to design a special customized paper glider. And again, I hope you understand that this is a very difficult, highly constrained problem. Very slight change in attachment angle changes the flight trajectory. So it's very difficult to design a very flyable gliders. So we provide integrated physical simulation into it to make it possible for everybody to design flyable thing. So let's see a video. So the first one is a failure case. So if you design arbitrary airplane, it doesn't fly, it just drops. And it's very hard to design. But here is a result using our system. We designed armadillo airplane, and then you get really fly well. And so that's a result. And our design tool is like this, the same idea. So user interactively edits the shape of wing and attachment angle positions. And then here's a visualization of flight simulation. This is a side view. So it starts from here and then fly. So this is failure case. It just go to up and then go down. So ideally, this glider should go all the way to the other end. And this many lines, many curves indicates variations. This is a hand-thrown glider. So we consider, it may be better to consider multiple trajectory at the time to see variations. And user basically edit the wing and shape, body shape, looking at the simulation result so that it actually flies really well. Yeah, it's getting better. It flies better. And then you change the shape, and you also change the position on the shape. However, in some cases, it's very hard to get really flying a glider by hand. So we put, can you read this? Make it fly. So if you press this button, and then system automatically applies optimization to this process, and then you will get a really flyable, glider. So watch carefully. As soon as you hit this button, system will automatically adjust the wing angle or position slightly. Yes, you see? As soon as you push that button, check mark, and then system adjusts the wing, and then you will get that. And this is more interesting. So the user manually drags the front wing, and the system automatically adjusts the rear wing. So this is interesting collaboration between human and machine. So the front wing is manually controlled, and this one is automatically controlled. And then system is always, reasonable shape. This is a weight. So after getting a design, it's easy to fabricate. Just send data to a laser cutter, and then you will get a shape. And then assembled manually, and then final result. So this is Armadillo one. So this is a launcher, and then this is our classroom, and then starts from here. It flies really well, and better than we expected. And then we are very happy with this result. This is a Stanford Dragon. It flies very well. It's fun project. That's it. And this work was getting reasonably popular, but people expect too much from this. As you engineers understand, this one doesn't make impossible possible, right? We just explore physically possible space easily. But like TV crew come to me and want to introduce this video, and they request us to create crazy things. And I have to tell, this tool can't fly anything fly. We only can do limited things. So that's an interesting story. And technically, interesting aspect of this project is we took data-driven approach.
So how do you decide which things the user can control and which things you'll optimize?
In that case?
Like you chose to let certain things be optimized and certain things to be controlled by the user, right?
Well, I think we don't do anything complicated here. I think in this case, if user is directly controlling something, it's controlled by user, and then system controls the other thing. And then just system picks the, steepest descent, most simple thing,
Right, but you could have varied other things, right?
Yeah.
The shape of the pieces
and
other things. So you had to make some decisions about what to keep fixed. And
ideally there should be more sophisticated mechanism, but in this particular implementation, we don't allow the system to change the shape. You just adjust angle.
Right, so how did you make the decision about what things you would allow to vary and what things you would you would keep fixed?
Well, again, in this particular project, particular implementation, changing shape is too high degree of freedom, so not good for optimization. So we took the easiest one, like just adjusting angle. But yeah, you are right. It's very important questions. Which one allow system to change, and which one should not be changed? That's future work.
Right. Yeah. I mean, it's a question about, you set up the HCI part by saying that we're trying to make things more I forget your exact term, but part of that is making these decisions about what's going to be under the user's control and under the system's control. Yeah.
Manish, are you looking for some sort of like design principle of how we make that trade-off?
Yeah, or just understanding how to make that trade-off.
Yeah, that's good. Thank you. Okay. Yeah, so again, technically interesting aspect of this project was we took data-driven approach. So previous systems like meta-formal closing, we just use standard analytic simulation methods. And also we tried standard fluid dynamic simulation for this project at the beginning, but it was way too slow, right? There's no way to predict the whole trajectory, multiple trajectory in real time for your real-time input. So we took data-driven approach. So where we fabricated many paper airplane actually, and then video recorded the flight trajectory, and then we estimated many coefficients for necessary for simulation, and then we get this data-driven approach for quick prediction of flight trajectory. And so I don't want to ride on an airplane, physical one, designed using this method. It's so inaccurate, but I think it's appropriate for designing a toy airplane, and I think it's sufficient and appropriate. Okay, so now next block is crowdsourcing. I'm hesitated to show this because you have an expert here, but I want to show at least what we tried. So so we worked on some computational design method with crowds. Partly inspired by lots of interesting work from your group. So I will introduce two projects from our group. So one is parametric design and one is shape modeling. The first one is parametric design. So the problem we wanted to address in this project is parametric design. And parametric design or parameter tweaking happens in many different applications. So one example is image editing. So if you want to edit image, you have to control many parameters like brightness or contrast or white balance, many things and many sliders, and it is very tedious for novice users and even experts, difficult to keep track of everything. So we want to help computational support. And also, this is another example, a material design or appearance design in graphics. If you want to have appearance like glossiness or color or many other parameters, and then it's very difficult. So we want to do it easier. And in this particular implementation project, we focused on crowdsourcing. So we decompose this complicated high-dimensional search task into simple microtasks and then ask crowd to work on it. Oh, by the way, I want to emphasize that same method can be applicable for self-sourcing. You can do it manually just by simple task rather than single big, massive, complicated task. So that's the thing. And of course, question is how to decompose a task into microtasks. That's the main problem. And specific contributions we claimed in this publication paper is first is Microtask Design, another is algorithm framework. So for the first one, we proposed a new method, and then we also implemented algorithm to achieve that. So the first one. So I think we believe the typical traditional approach to get crowd feedback is this kind of pairwise comparison. We show two samples in this huge parameter space and asked a crowd worker to pick the best one. I think this is a popular approach and reasonably works well. However, from the system's point of view, the information the system can get from this single input is very small. This is 1 bit information. And we thought, it's very inefficient. And then just by replacing this radio button to just slider, just very small change in UI, system can get much richer information from the user. So user just explore the parameter, one-dimensional parameter space using slider, one-dimensional subspace of the high-dimensional space, and then you can get one. And yeah, we expect that there's maybe slightly more overhead from user's point of view, but the benefit outweighs the slight increase of user overhead. So that's the idea. And then inside the system, we apply Bayesian optimization method. I'm curious, how many of you are familiar with Bayesian optimization? Everyone knows it, or roughly 1/3? Thank you very much. I didn't know this before this project, but this is a kind of established technique, and we extend this to support this one-dimensional subspace. So basic idea is to, the system gets estimation of the goodness or fitness in this high-dimensional parameter space. And then whenever you get input from the user, system gets some estimation and then decide which parameter space, one-dimensional parameter subspace to present depending on this current internal model. So this is kind of active learning kind of framework. So yeah, here's a kind of visualization. So this color-coded 2D. So this is a two-dimensional view of this. So yeah, this is actually high-dimensional, but this is 2D visualization, and this is this color-coded height field is invisible, unknown ground truth. So the goal is to find this place. And first, system randomly places some random one-dimensional subspace, and the user pick this point. And then system estimates the current guess is here. And then system puts another one-dimensional subspace in this space to get maximum information from the user. And then system controls the slider to get one. And then given this input, system updates the prediction and then presents the next one-dimensional subspace. And then user picks the best one in this subspace and then go to the next. And then eventually, by iterating this process, system gets better model and you will get a better result. So we did some evaluation. We compared our sequential line search and pairwise comparison and also four-way comparison. And then here's a result. And I think we were also excited about this result, which was better than we expected originally. So yeah, sequential line search gets much faster to converge and also combines the much better error compared to pairwise comparison or four-way sync. And this one checks the task completion time of each cloud worker for each task. And as we expected, the overhead cloud worker time for a sequential line search slider task is slightly larger than pairwise comparison or four-way, but it's not like double or triple. It's a little bit, and the benefit outweighs this overhead. So that's our result. Yeah, let me skip this later. Yeah, one interesting application is like this. We can request users to tweak appearance, material design task by giving this kind of natural language request to the cloud worker. So cloud worker was, for example, asked, please pick slider, adjust sliders as much as possible that the result looks like a gold. And then, cloud worker, each slider just work on a single slider, and then we accumulate it. And then eventually you get this kind of thing. So from the user's point of view, this is like a natural language interface for getting material design. Yeah.
So I would imagine that this works really well if you can ensure that the one-dimensional space you're exploring has like a single optima and not like several. Do you have some way of guaranteeing that? Like, are these linear subspaces?
Yeah, that's a very good point. So this is a perceptual aesthetic thing. So there's no guarantees that there's a single maximum. So that part is kind of weak. We just do it, assuming that some smooth space with single maximum. And yeah, treatment of multiple maximum that's not yet done.
If you see workers align on different local maxima, you can always just fork and explore both in parallel.
Yeah, that's possible direction to go. Yeah. But in this project, we assumed that simplified setting only a single maximum. That was assumption behind this. Okay, so another one is collaborative 3D modeling. And I must admit that this was not so successful project, but it was interesting, so I want to share it. So the motivation is 3D modeling is still tedious. I have been working on 3D modeling more than 10 years, 20 years, but still it's hard. So we thought it might be interesting as crowd workers to do it as a micro task. So that's a research question. So let's decompose 3D modeling into crowd tasks and then see what happens. So this is more like intellectual curiosity. I want to see is it possible or not and how good it is. So that's and then there are many ways, but we tested this very simple task. So suppose you want to design this kind of furniture from photograph. We ask crowd worker to sketch side view. In this case, this arrow mark means that please draw a front view of this chair. And then we provide a very, very simple, very basic drawing editor, just rectangle and oval. And then we ask user to give a 2D sketch. So this is a micro task. And each crowd worker only works on a single view. So there's no consistency between side view and front view and top view. So in this way, we collect many front view, many side views, and many top view independently. And then we assemble them together to get 3D shapes. That's what we experimented. And here's a kind of results. Like we asked crowd workers to draw side view, and then many of them correctly draw side view, but some misunderstand the request, completely random and very bad. So it's actually very challenging to get meaningful results from this kind of messy input from crowd workers. So we do many like a clustering thing and do many things, but still the result was like this. So we tried as best as possible technique like clustering or do our best, but from the initial result we got, this is the maximum we get. So it was too poor. We failed. So we implemented more iterations. So we integrated, this is, I think, very standard in crowdsourcing things, but we get evaluators, and then we picked good sketches, and we presented it to the next crowd workers as a good examples. Please see these examples. And then we get more data. And then we repeat this, and then we eventually get better result. And by integrating this mechanism, we managed to get better and better result. And after third iteration, we finally get the result. But as you notice, it costs a lot, actually. So that's the conclusion. So we managed to get reasonable shape with this is 3 iterations, 2 iterations, 5 iterations, 5 iterations. We get this, but it costs a lot. And we did test it, crowdsourced result, and then we also requested single expert to do it. And honestly, this was a failure. The cost was higher. And by the way, so we first submitted this work to Iowa USD, but we were rejected only because the payment to the crowd worker was too low. So we have to redo the study again with recommended price range, and then the cost was higher. So that was a reality. And also, however, so this is, the quality was higher by experts, the cost was lower for expert, but we found some benefit of crowdsourcing is around time. If you require higher expert, we need free time of this particular expert. Finding expert, it takes time first, and then the expert have to work on certain amount of time concentrate. It took time. So in this case, in this particular study, it took almost 1 day. But crowd workers, we can pick arbitrary person anywhere, so we get final result much faster. And also, human labor from user's point of view was much less here. It's almost fully automated. User just send request and then get.
Is time based on how long it took from when you started to have people draw stuff to when it finished? And for expert, is it the total time he was working on it, or total time?
Well, this time is where we or user start recruiting or send a request. And then the time includes all the time to find expert. And then the time ends when we get the result.
So what's the end-to-end goal here? Is it to take an image of a 3D model, a 2D image of a 3D model, convert it into different views of that model, and then reconvert it back to 3D?
Input is image or sketch or two-dimensional thing. And the output is 3D shape. So assumption is that we don't know the ground truth 3D model. We only have a photograph of something. Yeah, so 3D modeling from photographs, that's the task. This is subjective quality. Yeah, if you look this carefully, zoom in, lots of parts are missing here. So this is just qualitative subjective variation. Yeah, in this case, it's obvious. So many missing parts, consistency. Yeah. Yeah, so let me go back. So yeah, here it's almost automated. It's very easy to do. But here you have to negotiate, explain the task to the expert, negotiate, infer their skill from communication. So there are lots of communication. So I think we do have benefits. And yeah, maybe, yeah, that's the result. Okay, so finally, smart devices. So now we discuss about the fabrication, actual creation process. And again, typical pipelines like this. User designs something in computers, and then computer sends the data to the fabrication device, like 3D printer, and you get the final result. So this is a kind of one-way pipeline. So we want to make it interactive by having a smart tool. So user directly interact with a physical object with computationally supported tool. This may be very interesting. So that's the idea. And we are not the first of this kind. So we are certainly inspired by previous interesting works like computer-supported cutting machine or computer-supported milling machine. So human-computer work together to fabricate. So it's there already. So we did some different things. The first one is this one. I think it's self-explanatory from this photograph. But the first one is drawing system for carpet. Is it coming? Not good. Yeah. So yeah, inspiration is coming from here. So you can draw something on the carpet and you can quickly erase it. And then we implemented 3 devices. The first one is a raster display. So we put many rods, and then if you rotate, and they go up and down along the way, and then you can leave a trace, bitmap pattern, and then you can get interesting illustrations like this way. Yeah. So we call this a very environment-friendly display because no power consumption and there's no ink waste. It's reusable. It's very nice. It's very large screen, and it was fun. Yeah, it takes time, but it's. So that's one result. And next one is a vector graphics. So it's basically pen-type device. You arbitrarily drawing, and then the rotating wheel raises the far. And the most important part is orientation is stabilized. I hope you understand. But so yeah, however orientation you hold the pen, the tip is always be consistent orientation so that it always raises far. Whichever direction you go, which orientation you hold the pen. So it's a very high-tech device for carpet drawing. So if you use just a finger, you can leave a trace in one direction, but you cannot do in another direction. But here, you can always leave traces. So this is, again, interesting experience. This is like a carpet becomes a whiteboard. So you can draw whatever. And here is even more high-tech things. This is a remote, this is a speaker, ultrasound speaker array can produce force in distance. So you can remotely activate the far or erase the far. So yeah, this is too much technology for a simple thing. But it's a fun project. So yeah, that's it. Okay, so we are running out of time. So let me accelerate. So we also collaborated with architecture people to create huge one. So this is a fun project, millions chopsticks. So you see the scale. This is a person, and this is like a 4-meter tall, large scale pavilion made of chopsticks. And here's a pipeline. So this project consists of 3 components. One is a material design. So this is a composite of chopsticks and glue. And we tested many mixture and many different way of dropping. And we collaborated with professional structural engineers to see material property of this one. And also we built a dispenser, dropping glue and chopsticks together. And then we implemented a guiding system, combining a Kinect sensor and also projector to guide people to drop chopsticks. And then you eventually get this huge chopsticks architecture. And next project we worked on with architecture group is a huge scale 3D doodler. I think you know 3D doodler. This is a handheld 3D printer. You can trace 3D wire in midair. So we wanted to make a big one so you can see the scale. So people is here. It's a huge one. So the vision is like this. I want to draw a pillar here, and then you just do this, and you get a pillar here, and you can do this, and you get the next one. And this is the implementation. So it's actually dangerous. So this shape. But as you see, this device does create a pillar in midair. Yeah, it's not easy to actually draw free-form curve, but as you see, it does work. So what we do is just a standard form thing, rapidly solidifying form. And then, but if you do nothing, it just drops. So we wrap this with a mesh to stabilize, and then you can do something like this. Yeah, this is a fully experimental project. And I think this is the final one. Yeah, fabrication with natural shaped branches. So traditional building is built with very standardized, straight line pillars or wood materials. So in this project, instead, we want to leverage naturally shaped curved branches for architectural elements. This might be difficult in the past. However, we have now cheap 3D scanning and 3D milling machine. Combining these fabrication devices, we thought that it might be possible to use these natural shaped branches as architectural element. And here's a nice video. Yeah, this is an advertisement video. So we go out to collect natural shaped branches. Yeah, this is fun project too. Yeah, after this, yeah, and then fix on the floor, and then we do scanning here to get a 3D shape. And then after scanning, we move into the design process. We implemented a kind of gamification thing. The system provides feedback about the structure. And then we send it to the milling machine. The system automatically computes the joints. And then we get our result here. So this is an initial experiment, so we cannot do complicated things. So we are still ongoing project, so we try to build large one based on this kind of technology. So yeah, so that's mostly it. So we are working on human-in-the-loop computational design for end users to design something with physical simulation and crowdsourcing and smart devices. And yeah, so just briefly want to advertise our current work. So we are staying away from machine learning for a while, but now we started working on HCI for machine learning. I just heard the similar thing is happening here, James and other people working on, but I try to do something like that. And the goal here is to making machine learning easier to use. So, I have been working on making computer graphics easier to use for novice users. So I want to do similar thing for machine learning. So currently, if somebody wants to use machine learning system, build system, it's better to hire a machine learning expert or at least some knowledgeable person. But I hope people can more easily can use machine learning techniques. And here's a different view. So there are many people using machine learning for HCI application, like a gesture recognition, activity recognition, many vision tasks. But that's not what we want to do. I want to do more like the opposite direction. Even if machine learning may do many things automatically, but building machine learning system needs lots of human intervention, human efforts. So we want to develop tools to help these people using machine learning. So yeah, that's the idea. So yeah, there are many factors like help people to get data for machine training, and also interface to help control learning, and also help user interface actually using and adjusting the result of machine learning operations. So this project just started, and we are hiring. So that's why I'm here all the way. So if you are interested in this kind of project and want to spend some time in Tokyo, we are always expecting visitors, interns, postdocs. So please come to Tokyo. So thank you very much for your time. Okay, that's it. Yeah.